Welcome back, everyone. While I have a bonus video for you guys today, I would like to go over the material in Chapter 29, even though you're in the spring term of 2020, with all of the nonsense we've all had to put up with, you will not be responsible for the material in Chapter 29. Not on exam number 4, not on the final exam either. Which is a shame that that's what I wound up having to cut, but I figured that was the easiest and sort of most direct and least violent way to drop a week of material from the term. But it's a shame because I know a lot of you are quite interested in biochemistry in general and metabolism in particular. And I feel like the great thing about this chapter, for those of you going on to biochemistry, is it lays the foundation for you to understand all of these reactions of this type that are responsible for the continuation of life as we understand it, as just applications of what we've talked about these 2 semesters in Organic Chemistry 1 and Organic Chemistry 2, because I need to tell you that the chemistry of life is what we've learned these 2 semesters. Naturally, it doesn't look the same. Some of the actors are dressed in different costumes, maybe you might almost say. Certainly, the molecules are a lot larger than the ones we dealt with in class. But conceptually, there's nothing here that you can't understand as something we've already covered. So the only things that differ are the details, such as, again, the size of the molecules, and then enzymes are, of course, another big thing. We've said before, once an enzyme gets involved in the mechanism of a reaction, all bets are off. And all sorts of things might happen in a concerted fashion that normally we wouldn't expect to happen. So that being said, while you might get into enzyme mechanisms when you get to biochemistry, goodness, in the 30 years since I've graduated from college, so much has been learned about enzyme mechanisms that they simply didn't know back when I was in school. But that being said, I think for our purposes here, just going over the material, I don't think you need to think about these reactions any differently than we did last semester or this semester. And I think all of this is good review for the final exam as well. So even though this material per se won't be on our final exam, I think it does no harm to take a look at this material. Yeah, I think that's all I really need to say about that. I put up here, even if you were responsible for this material, of course, I would be saying you do not need to memorize all of these molecules and pathways. You certainly will have to if you go on to biochemistry. In fact, memorizing these pathways, all of the structures of the molecules in it, all of the names of the enzymes that catalyze all these reactions, if it's anything like my experience with biochemistry, that's going to be the main thing that they focus on. How much easier, though, to learn it when you understand the reactions behind it. And I think organic chemistry, looked at that way, is very good background for biochemistry. It's not just 2 semesters that you have to endure somehow in order to go on to what you really want to go on to. But you can use what you learned these 2 semesters in order to help you understand these reactions, not just memorize them. There's going to be a lot of memorizing anyway, I think, when you get to biochemistry. And maybe that's fine. But the feedback I get from former students, even in just about 5 years I've been at A&M, so far the feedback I'm getting is, indeed, this is very good background for the biochem class. So basically what I'd like to do here is go through the more famous, let's say, of the pathways that Chapter 29 goes over. I'm not going to cover the entire chapter, but there are some of these pathways are so important that they just really need to be mentioned. And one such idea is the idea of getting biochemical energy through metabolism, which I think we all understand, even if we're just someone who has had high school biology. We understand that you need to get energy somehow in order to run our bodies. And that's because a lot of the reactions that we depend on for life itself are endothermic. And so we need to get energy in order to drive those reactions forward. I said endergonic, that might be a better way of putting it. But be that as it may, you're probably aware that we get a lot of energy by the hydrolysis of ATP. Let me see if I can't make this a little bigger. Ooh, that's much better, isn't it? If I do say so myself. I mean, why be staring at these tiny little things? So you have no doubt been told in various lower level biology classes that this phosphorus-oxygen bond in ATP, which I'm here representing without drawing out the entire adenosine system, the sugar and the nitrogen base, that's all still there. But we'll just focus here on the triphosphate group. And so these phosphorus-oxygen bonds, I know you have had teachers in your past, because I certainly have too, that told us that this was a high energy bond. And that is exactly correct. That's exactly what that is. And so the way we get energy from ATP is by a hydrolysis reaction. This, by the way, is another really very cute device that biochemists use. Largely biochemists, though sometimes other types of chemists do too. But what they mean by this, it's a shorthand showing that water comes in and reacts with this guy and spits out H+ as a byproduct. And sometimes you'll also see just the arrow going into the reaction arrow with nothing else coming out. That means it all gets added in and there's no byproduct. Other times there's kind of an elimination reaction. You'll just see an arrow coming out showing the side product, and then we'll continue on to the major products of interest. So what happens is the water molecule reacts at this high valent phosphorus atom. And the mechanism is probably sort of nucleophilic acyl substitution-like. I don't think it's SN1 or SN2, but be that as it may, what we wind up breaking that bond, and when we do, we get our this you could consider to be HPO4 2-, or in your biology book, they'll call that PI, for inorganic phosphate. Whichever way you want to look at it is totally fine. And over here is our ADP. And we get a fair bit of energy out of that, about 30 kilojoules per mole each time we do that hydrolysis reaction. And what I really want to point out is this is not a new or different thing. We saw this exact same kind of chemistry in chapter 21 when we covered nucleophilic acyl substitution reactions. We could just as easily say that this carbon-oxygen bond in a carboxylic acid anhydride is a high energy bond. And this will also react with water and effectively spit out H+. And if you want to think of it that way, you wind up with two carboxylic acid molecules. I'm just here keeping the charge balanced, essentially. But my point here is this reaction is the same thing as this one. And if you understand this reaction, which I hope we all do after chapter 21, then we know all we need to know to understand this. And this also is a reaction that will liberate energy. I don't know if it'd quite be 30 kilojoules per mole, but it certainly would be exergonic as written. So much for how it is that we get energy from ATP hydrolysis. I also want to talk about fatty acid breakdown and the opposite, fatty acid biosynthesis. But in order to be able to break down fatty acids, first thing we need to do is hydrolyze a triglyceride. And we're already familiar with the structures of triglycerides. Of course, we can consider 3 water molecules coming in, spitting out 3 H+, and giving us 3 carboxylate ions. Or if you want to think of the proton as still attached to the carboxylic acid, it depends on the pH, right? Whichever way you want to think about it, that's fine. I'm just sort of drawing it the biochemistry way. But here's your 3 fatty acid molecules, and those will go into fatty acid breakdown, and that's how we get energy from fatty acids. But the other species here is nothing other than glycerol. And I've kind of cutely drawn it here in a Fischer projection, even though this molecule is not chiral. But glycerol is also metabolized, and it's metabolized using reactions that we can well understand. The first reaction that glycerol undergoes is a selective phosphorylation, and again, it uses ATP to do that. And it winds up putting the phosphate group only on this carbon. So that reaction is stereospecific, because now this carbon is chiral, right? And another feature that you'll see again and again and again in biochemistry, which is fascinating and strange and frustrating all rolled into one, is now that we've gone to the trouble of making this chiral center, we immediately ruin it by oxidizing the secondary alcohol to a ketone. And NAD plus is a very common biological oxidizing agent that will do that for us, with NADH being the corresponding reducing agent. But this acts very much the same as PCC or even desmartin periodinate. So you can review the concept in chapter 17, which we covered the first term. And so from this we get DHAP, dihydroxyacetone phosphate. And that's something our bodies know what to do with. So, glycerol itself is metabolized. What about these fatty acid molecules? Well, it turns out that they get broken down 2 carbon atoms at a time. By the way, let me just tell you a little bit about how these class notes are set up. When I first made my lecture notes and class notes for chapter 29, I started with the best of intentions. And actually, in the original one, these were blank. I've uploaded new versions that actually have the structures in there. But I started out at the chalkboard with my chalk like a good little teacher, and got through as far as this. And then I started getting a little bit lazy, and I started also thinking of the students that they're going to get tired from writing down all of these structures. So then I started to make structures in ChemDraw, and I did that through fatty acid metabolism. And then I just gave up entirely and started putting in what was just absolutely cut and pasting from the textbook. So that's why you see it going like this. That was my original way of thinking. So fatty acid breakdown, like we said, this is going to get broken down 2 carbon atoms at a time. And each of those 2 carbon atoms will go into an acetyl group. Acetyl groups and acetate ions, things like that, are things our bodies know what to do with. And all of the reactions in this pathway are reactions that we in principle understand already, at least conceptually. The first step is an oxidation reaction, by which we oxidize our fatty acid at the alpha and beta carbons to make a new carbon-carbon double bond. You can see also that the fatty acid is carried as a thioester on coenzyme A, and that's quite common also. So there's ways of hooking and unhooking acyl groups to coenzyme A. So coenzyme A rears its head quite a bit, as I'm sure you're already familiar with it, those of you who've taken even any biology recently. So this oxidation reaction can really be thought of as maybe the exact opposite of a catalytic hydrogenation. And indeed, the reducing agent, the flavonine adenine dinucleotide reducing agent, is very, very much like catalytic hydrogenation, most of the time. So the oxidized form, FAD, will do the opposite of it, and it will dehydrogenate this compound rather than hydrogenating it. So we get this alpha-beta unsaturated species. After that, water adds, and we already know from chapter 22, maybe. Actually, I think it was 19. It might have been 19 and 23 that we covered the idea of conjugate additions. We said that there are many nucleophiles that, given the choice of adding at the beta carbon or adding directly to the carbonyl, would rather add to the beta position. And water is one of those nucleophiles. And so we get this species here. I was a little bit lazy here. Of course, this generates a chiral center. Not that it matters, because the very next thing we do is wipe that chiral center out, right? We use now NAD plus as our oxidizing agent. NAD plus you can think of as being very much like PCC or chromium trioxide or one of these types of reagents. And so it will oxidize the secondary alcohol to a ketone. And so I don't even know what the chirality or what the configuration is at that chirality center. It doesn't matter in my mind, because it immediately gets oxidized to an sp2 hybridized carbon and game over. It's not chiral any longer. At this point, another molecule of coenzyme A comes in. It will attack the ketone carbonyl, and this will do the exact opposite of a Claisen condensation. It simply runs that mechanism in reverse, and you wind up getting two pieces, one of which is acetyl coenzyme A, and the other of which is another another coenzyme A thioester that's 2 carbons shorter. This now goes back up in the top and gets fed back in, and you get another acetyl coenzyme A, and this happens again and again and again and again until you have nothing other than acetyl coenzyme A molecules. So that's how fatty acids are broken down and how that we get energy from them. What about the opposite pathway? What if we need to store energy in the form of fat? That is much like the reverse of the reaction we just covered, but not exactly. It's not a literal, exactly backwards version. There are other things that the pathway needs to include in order to go forward. But the pathway does start with acetyl coenzyme A. The first step is intriguing. It couples hydrolysis of ATP to ADP with a bicarbonate ion coming in. And you can think of this as contributing also to the hydrolysis here. And what that winds up doing is adding the equivalent of carbon dioxide onto this methyl carbon. That's not surprising. We already know that the hydrogens, the protons on this carbon, since it's alpha to a carbonyl, those protons are slightly acidic, and so we would expect this carbon to be nucleophilic, and we could imagine it adding into CO2 much like a Grignard or alkylithium reagent would. So we covered that, I think, in chapter 20. Double check me on that, but that was one of our ways of making carboxylic acid, carbonation of Grignards or alkylithiums. So this reaction really is not that much different from that. And it's, again, coupled with ATP hydrolysis, so we get the energy to run the reaction. The next two steps are a little odd, and I'm only including them for the sake of completion, because I don't want to lie to you. They don't contain ideas that are critical for us. I'm sure, though, that if you go on to biochemistry, your professor will be very, very interested in these details. So certainly don't slack on them when you get to that point. But this first step is nothing other than a transesterification, or if you really wanted to be picky, a transthioesterification, in which something called acyl carrier protein, ACP, which also has a sulfhydryl group, just like coenzyme A does, attacks the carbonyl, and you get O-, and then we lose acetyl coenzyme A as the leaving group. And so now this acyl group is on the acyl carrier protein. This now reacts with yet another thioester. R is just a third thing that gets attached to acetyl groups. So not coenzyme A, but kind of like it. And this reacts with this species. Not surprisingly, you've got an activated carbon here, right? These protons are between two carbonyls, and so extra acidic. So we would expect that carbon to be nucleophilic, just like in a malonate ester or acetoacetate ester synthesis. And so that can act as the nucleophile and add into this thioester, and in so doing also lose carbon dioxide, and we get this ketoester shown over here. So the thiolate ion and carbon dioxide both get lost, and we get this species here. This then gets immediately reduced, not in this case by NADH, but by NADPH. Again, not a big deal for us, but you will. I can almost guarantee you will need to memorize those particulars when you get to biochemistry. For now, don't worry about it so much. But would just be aware that this is a reducing agent, very much like sodium borohydride. And if we treated this thing with sodium borohydride, we would expect it to reduce the ketone and not touch the ester. And that's exactly what happens here too. Once again, I've been lazy and not indicated the stereochemistry. This reaction is stereospecific in the cell, right? You get just one of the two possible alcohols here. But again, it doesn't matter. This is immediately dehydrated. There are dehydratase enzymes that do that for us, and the carbon goes back to being sp2 hybridized anyway. So you just get the unsaturated thioester, which once again gets reduced. I will let you know, this always surprises me every semester. I believe that you will find when you get to biochemistry that FADH2 is the thing that's most like catalytic hydrogenation. And so if you had covered that up, I would have expected this to be FADH2 going to FAD. Instead, it's NADPH and H plus going to NADP plus. Either way, we reduce the carbon-carbon double bond to a carbon-carbon single bond. And look, now we've attached 2 more carbons onto our acetyl group. This then goes back to the beginning and finds another acetyl coenzyme A, and on and on and on it goes. So this is how we build up fatty acid molecules. There are many other pathways in chapter 29 that if we were including at this term, I wouldn't be going over those. I really want to go over only the ones that I think first come to mind. So we'll also do the citric acid cycle or Krebs cycle, which, gosh, everyone's heard of that who's taken high school biology. And also glycolysis. I can't leave out glycolysis. Glycolysis is too important. And good news on both of those, we're going to find, if not every single reaction here, at least most of them look like something we've done these 2 semesters of organic chemistry. And in the Krebs cycle or citric acid cycle, this is how we metabolize the acetyl groups in acetyl coenzyme A. And in the first step, we react the oxaloacetate ion. Oxaloacetic acid would be this with 2 CO2H groups. So since we're at pH 7, that's going to be below the pKa, above the pKa's of those 2 carboxylic acid groups. So that's why they always stress so much that it's oxaloacetate and citrate and isocitrate. Why all the eights? Well, it's because all of the carboxylic acids at biological pH are going to be deprotonated. They're going to exist in the form of their conjugate bases, the carboxylate ions. So that's why you get 8 everywhere. Anyway, oxaloacetate, I think if you look at this molecule, I hope you're all focusing on this carbon here, which is again between 2 carbonyls. And so you would expect this carbon here to be nucleophilic, that it could be deprotonated effectively and make an enolate ion, which can now attack the carbonyl of an acetyl coenzyme A group and expel coenzyme A as a leaving group. And so what you wind up getting out of this is a molecule of citric acid or citrate. And that looks like this. This then undergoes a dehydration first to put a double bond here. And we learned about dehydration reactions of alcohols to give alkenes. That would have been back in chapter 7 or 8 or something like that. And then that double bond is rehydrated in the opposite direction so that the OH goes over here. That gives you isocitrate. Again, and then diastereomerically pure. So you only get this alcohol, not that it matters in the sense, it does, but it also sort of doesn't, because we're going to oxidize that immediately with NAD+. Carbon dioxide gas also gets released. We've seen decarboxylation reactions before, and it oxidizes it to this, this alpha keto carboxylate ion. That's alpha keto glutarate. And again, for our purposes, I wouldn't even be asking you to memorize the names, but I would expect you to go, oh, NAD plus is going to NADH and H plus. That's an oxidation reaction. And no wonder we're going from a secondary alcohol to a ketone. To a ketone. And that's a reaction we've seen before. This species then gets thiolyzed by acetyl coenzyme A. That's not surprising. We know the thiol is an excellent nucleophile that can attack the carbonyl. At the same time, this is just goes to show you how strange enzyme reactions sometimes are. At the same time, this decarboxylates, and you'll find if you try to work out the mechanism that you're left with an extra electron pair that you need to put somewhere. You know, if you try to work out a reasonable mechanism. So where's that extra you can't just sort of shoot out an electron pair into space. It is to go somewhere. And indeed, where it goes is NAD+. NAD+ acts as an oxidizing agent, accepts that electron pair, and gives off, along with the carbon dioxide, NADH and H+. So all three of those things happen essentially in this step. And the end result, when all the dust clears, is succinyl-CoA, coenzyme A, which is this structure. This then reacts with an inorganic phosphate. I guarantee you your biochem professor will make a big deal out of this, because we wind up reconstituting GTP, which is an ATP alternative, right? By using with an inorganic phosphate. And that is kind of a big deal, that you're able to rephosphorylate the equivalent of ADP and go back to the equivalent of ATP. We also lose our coenzyme A molecule, and you get a molecule of succinate. So that's a big deal in terms of the energetics of reactions. Not really what we're focusing on here. I just kind of want to put it in the back of your head somewhere, so that when your professor makes a big deal out of it, and I guarantee you they will, you know, oh yeah, we saw that before. Anyway, the organic product is succinate. Succinic acid is one of our dicarboxylic acids again. That's the such of, oh my such, good apple pie, sweet as sugar. This then will get oxidized. And this really is what I most often would see FAD doing. FAD acts as the opposite of catalytic hydrogenation. And FADH2, if it were going in the other direction, acts very much like hydrogen on palladium. So the end result is, maybe not too surprising, that we get the trans double bond. That's fumarate. And fumarate then has this carbon-carbon double bond. Water will add quite easily. It's adding basically to the beta carbon of a carbonyl, whichever way you want to look at it. You do get exclusively the S isomer that you see over here, and you guessed it, not in a sense, not that, I mean, it matters a heck of a lot, but in a sense, not that it matters, because we're going to take our NAD+, which is the equivalent of a chromium reagent or a desmartin priodinane, and oxidize the secondary alcohol to a ketone to give us oxaloacetate, which is where we started with. That then brings in another acetyl coenzyme A molecule. And so one by one, the two carbons in the acetyl group wind up getting kicked out as carbon dioxide. Let's see, here's one, and here's another one. So that's the fate of the acetyl groups in coenzyme A. Last but not least, for my very last trick, we'll go through glycolysis, and I hope to convince you that this also consists of nothing other than reactions like unto we've talked about in your 2 semesters in organic chemistry. So here's glucose in the alpha anomeric form, D-glucose. And just so when you look at this diagram, which again, I totally plagiarized right out of your textbook, what they're doing here is they're showing you the sugars both in the straight chain form and in the cyclic form. Just you know, you have both ways of looking at it, so you can make sense of it using either one. The first step is a phosphorylation step, and the phosphate group will go with this particular enzyme anyway, in particular onto carbon 6, onto that last OH group, and you can look at it either way here. So they were very naughty and left off the hydrogens, weren't they? That was naughty of them, but oh well. The next step is a tautomerization reaction, in which we will go through the so-called enediol intermediate by forming first the enol of this aldehyde. The resulting species you can call an enediol, because the double bond will be between two carbons, both of which have an OH group, hence the name enediol. And so that will then tautomerize again, this time putting the carbonyl group on carbon 2. And so we've essentially isomerized glucose to fructose. And you can look at it either way. Both are correct ways of drawing fructose. Fructose is a ketohexose. This then gets phosphorylated again, so goodbye to another ATP over here in carbon 1. And this species, which with 6 carbons, is now ideally set up to do the opposite of an aldol condensation. So you could call this an aldol cleavage, and it's going to break this bond right here. And you simply run the mechanism of the aldol condensation in reverse, and you get 2 pieces, one of which is dihydroxyacetone phosphate, which we met just earlier, and the other of which is glyceraldehyde 3-phosphate. And again, that's our old friend D-glyceraldehyde, because that's, again, the natural one, phosphorylated in carbon-3. Dihydroxyacetone phosphate can do the exact same thing that we did to go from glucose to fructose. It will tautomerize to the enediol, and then the enediol will tautomerize again to leave the carbonyl on carbon-1. In other words, as an aldehyde group. So in the end of all of this so far, and we're only halfway through the process, I think, but at this point we have ourselves 2 molecules of glyceraldehyde 3-phosphate for our original glucose molecule. Glyceraldehyde 3-phosphate is something our bodies well know what to do with. And what happens is a concurrent oxidation. So we're going from NAD plus to NADH. That's like a chromium reagent. It's as if we oxidized the aldehyde all the way up to a carboxylic acid. And alongside, surprisingly, along with that comes an inorganic phosphate ion, so HPO4 2-, and we get the acyl phosphate. That's a red hot species. Acyl phosphates are sort of like acid chlorides, so very, very reactive. That molecule happens to be called 1,3-bis phosphoglycerate. And the reason they use the bis is because if you said diphospho, it sounds like a diphosphate group, you know, the 2 phosphates hooked together, but it's 2 individual monophosphates, so that's why they call it that. The more you know, right? That's, again, another thing your biochemistry professor won't tell you. Be that as it may, at this point, we can use the very high energy acyl phosphate to rephosphorylate ADP to ATP, and that's what happens here. And so you get now 3-phosphoglycerate. This now is essentially an isomerization such that the end result is the phosphate gets transferred from carbon-3 to carbon-2. And I don't know this for a fact, but I wonder if that's intramolecular. I think that might be a 5-member transition state. 1, 2, 3, 4, 5. I don't know that. I'm not familiar with the mechanism, but it's possible it goes through a 5-member transition state. Even if it doesn't, there's an enzyme that grabs it just right, of course, and makes everything to happen exactly as we want it. So now we have 2-phosphoglycerate. This can then be dehydrated. So here's your water coming off. And we lose water across these 2 carbons. And this gives you the phosphate ester of an enol. So phosphoenol pyruvate. If your biology professor was like mine, they said phosphoenol pyruvate, PEP, and it is indeed a peppy molecule. Very, very high energy, very unstable, because again, it's the phosphate ester of an enol. And so we can take advantage of that by rephosphorylating another ADP. And then you'll effectively get the enol, which will tautomerize to the ketone, which is, again, a familiar reaction to us. And so that's how glucose is metabolized. You wind up with a molecule of pyruvate, which is, again, another very familiar molecule. So I hope that was at least interesting to some of you. I wanted to get that out there because I figured it would be. I also had some selfish reasons, I will admit. This way I can now focus on writing exams and grading exams because I've really got all my lecturing done. And also, since, as you've heard me say, biochemistry is not my forte, I didn't want to go through an entire year without having myself gone through this material. So other than that, that's just a taste of what you'll find in metabolism. And other than that, again, trust you all are staying well and safe. Have a good day.